A pragmatic case for static typing. Thanks.
Hello, hello, hello. Are we on? A bit closer. A bit closer. This good?
Yes.
Hello. So this is a pragmatic case for static typing. If you've ever talked to Haskell programmers, OCaml programmers, they're probably all going, oh, static typing is the bee's knees. So sort of my opinions as to why this is so. So the slides are available. I'll show this slide again towards the end so people can see it. One request I have for people, this is a very contentious issue, so if you can hold your comments, objections, criticisms, etc. to the end. We have a limited amount of time. If we start getting derailed, we will never end. So, who am I? Why can I give this talk? The important things about my resume are I've been paid to work on both 50, it's actually more than 70 now, 1,000-line Clojure code bases and 250,000-line plus OCaml code bases. So I've been on both sides of this argument. I've seen both sides of the issue. So I want to start by going, what do I mean by pragmatic? I emphasize pragmatic in the title. What do I mean by that? It's very easy to find people who have different definitions of words. So I want to define my terms first so we don't end up arguing what the meaning of is. The thing to remember is programming is a means, not an end. Our goal here is to solve problems. Working code solves we use working code to solve problems. We do programming to get working code. I'm a programmer. I'm not a mathematician. I'm not a philosopher. I don't worry about the perfect, the full abstract definitions of stuff. What I'm interested in is solving problems. And that's what I mean by pragmatic, is does this help solve problems? So the only thing I'm really interested in for programming languages and for all tools, in fact, is time to working code. Whatever helps us solve problems faster is good. Everything we care about in programming languages and all tools we care about because it affects this number. We care about it because it helps us solve problems sooner. If it doesn't impact this number, it's at most an opinion or a taste. And by working code, I don't just mean written. Seems like a lot of programmers have the philosophy that once you hit save, you're done. You're not done. By working code, I mean written, compiling, debugged, documented, maintainable, the full life cycle of the code. Not just the stuff that costs, the stuff that you have to pay now, but the stuff that you will be paying 5 years from now, maintaining the code. So my point is, static typing reduces time to working code. This is the most important slide in this whole presentation. This is the point I'm trying to make. Everything else in this presentation is just why this slide is true. Now, next term I want to define. What do I mean by static typing? A lot of people, when I start talking about static typing, go, oh, I know what you mean. You mean Java, you mean C++, you mean C#. No, I do not. These are all languages that have Algol 60s type system with some extensions tacked on, which is over 50 years old by this point. What I mean by static typing, when I talk about static typing, what I want you to be thinking about is languages like standard ML, OCaml, F#, but most importantly, especially for this presentation, Haskell. Most of what I say will apply to all of these. I will be doing the examples in Haskell both for the the obvious reason and for the reason that I can actually say stronger things in Haskell than I can in any of these others. Come on. So now, with an actual solid definition of what we're going to be talking about, what point I'm trying to make, now we can get into the rest of the talk. I want to start with the little things. As static typing enthusiasts tend to do, we tend to like to go to the fancy stuff, the GADTs, the higher kinded types, the dependent types, etc. But it's really the little things that just affect you day in and day out that I think make the biggest impact. So static typing reduces the time to find and fix simple bugs. Most bugs are simple. If we can reduce the amount of time we take to find 90% of the bugs, this is a good thing. So when you go and compile a Haskell and it gives you a type error, the type error gives you that an error exists. This is a non-trivial and important piece of information, I comment. The file the error is in, what line the error is on, what column it starts in, and a hint as to what the problem is. Now, there will be times when the compiler will be off by, I've seen it off by tens of lines as to where the error actually is. And we could definitely use help on making our error messages much more understandable. But it gives you some hint, it gives you a place to start. So the time to actually fix most type errors is actually dominated by how fast can you get to that point in the file. How fast can you load the file up and get to that line? You look at it and you go, that's the problem, and you fix it immediately. So you're looking at tens of seconds to fix the error. I have, on occasion, had to stare at a piece of code for tens of minutes to figure out what the compiler was complaining about. This becomes less common as you become familiar with, oh, the error is this, that means this is likely wrong. But it still happens. So worst case, you're looking at tens of minutes. On the other side, an error given to you by unit testing, dynamic type people will generally go, oh, you don't need static typing, you find the same errors with unit testing. But even finding the same bug, unit testing gives you that the bug exists, again, useful information, what module or class the bug was detected in, the manifestation of the bug, how things go wrong, a stack trace, maybe if your language supports it, and the ability to reproduce the bug. And that's all. Now, welcome to the debugger. Welcome to stepping through your code just to try and figure out what's wrong. So the average time it takes to at least for me, to fix a testing error, it's not unusual for me to take even minutes to find and localize a testing error. And in the worst case, it's easily hours of stepping through code and staring at things trying to figure out what's wrong. Just firing up the debugger and running the test suite can easily take minutes. So the thing to remember here, tens of seconds, less than minutes, tens of seconds to tens of minutes is less than minutes to hours. So every error we can move, stop that. Every error we can move out of this category, out of the right-hand side, onto the left-hand side, wins us time, brings the time to working code sooner. So, part B, static typing eliminates null pointer exceptions. Now you may laugh, but there's more than one day that this alone makes static typing working, in my opinion. Tony Hoare, by the way, who invented null pointers, calls them his billion-dollar mistake for all the time that has had to be spent tracking down null pointer exceptions. So how does Haskell eliminate null pointer exceptions? Very simple. It has no such thing as a null value. If you're given a list, you will be given a list. It may be an empty list, but it will be a list. If you're given an int, it will be an int. If you're given a string, there will be a string. Maybe an empty string, but it will be a string. So how do you represent values that are not there? For those who actually know Haskell, I'm actually going to dig in a little bit to some very basic Haskell for the new people. So bear with me, you old hands. How do we represent a data that isn't there? Haskell has this idea called a maybe type. So a maybe type holds any type of type A. So you can have a maybe int, or maybe string, or maybe a function to int to string, or whatever. So a maybe of type A, stop that, hitting the wrong button. Maybe of type A, there are two possibilities. It is either just a value of type A, or it is nothing. Nothing is our null value, just as our non-null value here. So maybe actually works a lot like list here if you think about it. You can have a list of int or a list of strings. Maybe works the same way. So the nice thing about this is it's expressly stated in the type what values are optional and what values are not optional. So for example, here is the type signature of our function find. Now find takes another function that takes some type A and returns a Boolean, and it takes a list of type A and it returns some maybe A. If there's an element in the list that this function returns true, the first one, it returns just that value. If the list is empty, or if there's no value the function returns true to, it returns nothing. The interesting thing here to note, however, is that only this value is optional. When it says here, I take a function, you don't get the option to not pass a function in. This is not a maybe type. You have to pass a function in. Only the types that are explicitly declared nullable, or in this case maybe, can be not there. So another important thing is the type maybe int is not equal to the type int. So if you just called find with some function on a list of ints, let's say, and wanted to add 3 to the result, this is a type error. Haskell would not compile your program. It would sit there and go, you're using a maybe int here and you expect it to be an int here. Fix your code. So how do you use it? Well, how you use it is you do what's called pattern matching against it. So once again, we call our function find, and we pass it into the case statement. The case statement's sort of like your standard switch statement in C and Java and etc., except that it also binds variables. So in the case where we actually find a value, this function returns just the value. So this line matches, and x gets bound to whatever value it found. At which point we can use it just like x is an int here, so we can just add 3 to it. Also, we have to deal with the case of what happens if it doesn't return a value? What happens if it doesn't find a value? At that point, we have to return some other value, and I'm just returning 77 here because, well, it's random code, no one actually cares. Note that x is scoped. X only exists in this expression. It doesn't exist down here. So the nice thing about this is Haskell actually does exhaustiveness checking. And if you forgot this line here, Haskell would remind you with a warning going, you're not exhaustive, you're not testing the case, nothing here. So Haskell basically finds all the places you need to do null pointer checks and make sure you actually both check for the null pointer and deal with the case where it is null. Note, you could just as easily throw an exception. So if a null pointer exception really is the right answer, you can re-implement that if that's what you mean. But note, you have to explicitly say, here I expect a null pointer exception. So part 2, I want to talk a little bit about large-scale programming. Now, large-scale programming is different. A lot of programmers seem to think, at least in my experience, that all programming is the same. And that is not true. But what do I mean by large scale? I mean lots of code, tens of thousands of lines, long-lived, be around for years, many developers, 3 or more. This isn't, by the way, this isn't brag-worthy code. This is where I start seeing the large code effects start kicking in. And it is very much language and team dependent, but this seems to be, at least in my experience, fairly consistent about where it starts being a large code problem. Not all programming is large scale, and that's okay. I don't mean to go, there's real programming and toy programming. That is not my intention at all. Actually, I would consider, in aggregate, small-scale programming, the one-off shell scripts people write and the small programs people write, in aggregate, probably have more value than the large-scale programs, simply because they are that much more numerous. But some programs are large-scale, whether we want them to be or not, and we have to deal with them. So what are the problems with large-scale programming? Well, the first problem was don't do that. There's that old joke, people have probably heard it, of the guy goes into the doctor's office and goes, "Doctor, it hurts when I do this." And the doctor looks at him and goes, "Well, then don't do that." That seems to be our response in a lot of cases to pain points in other languages. "Doctor, it hurts when I forget to free memory. It hurts when I dereference an old pointer. It hurts when I pass a string in where an int is expected." Well, don't do that. Well, in large-scale programming, don't do that doesn't work. The problem is idiot programmers. And by idiot programmers, I want to be clear here. By idiot programmers, I'm using a technical definition of idiot. I mean the type of programmer who, when you tell them don't do that, goes and does that. Now, Brian's observation, named after possibly the best programmer on the planet. At 3 people on the team, there's a 50% chance that at least one of them is a full-time idiot. And as the team grows larger, the probability of not having an idiot goes to 0 pretty dang quick. And by full-time idiot, I mean the person who does what you tell him not to do on a regular basis. They seem, in my experience, by the way, to fall into 2 categories. One category is the "I didn't know it was loaded" category. The other category is the type where when you tell him don't do that, he gets a look in his eye like "challenge accepted." And you know he's just looking for an excuse to go do that. So you might go, okay, you got an idiot on your team. Fire the idiot. Get him off the team. Right? Well, there are 2 problems with this. The first problem is one person's idiot is another person's genius. The second and much bigger problem with this is we are all idiots some of the time. It was late, I was tired, maybe a little drunker than I realized, but the schedule had already slipped badly. We needed a fix quickly. So I didn't think about things as carefully as I should have, and just this once, because it seemed like a good idea at the time, yeah, and now we're the ones doing that. So static types turn "don't do that" into "can't do that," or "can't do that wrong," "can't screw that up." So an example to show you what I mean. This is a hunk of code in Clojure because I can bang out Clojure without thinking about it. I could write just as easily in Ruby or JavaScript or language of your choice. This defines a function called EX. An EX takes 2 parameters, a B and an X, because I'm a functional programmer and all my variables have one name and Java programmers hate me. So I go, if B is truthy, I take X and I assume X is something I can add 3 to, so I add 3 to X. Otherwise, I assume X is something I can apply values to, a function or a map or something similar, and I apply the number 3 to this. Now, I've had a number of times people tell me to my face they need to write code exactly like this. If they can't write code like this, they can't program. So, and this is true to a certain extent. There are times when you need to pull stunts like this. So how do you do this in statically typed languages? How do we change this so you can't do that wrong? So I'm going to introduce to you another type. This is the either type, another standard type in Haskell. Again, for your old Haskell hands, bear with me. This is a newbie talk. This, unlike the other type, unlike maybe and list, this actually takes two type parameters, A and B. And its values are either left of some value of type A or right of some value of type B. So I can now sit there and I can rewrite this function. This is the same EX function as on the previous slide, except written in the Haskell manner. Except it only takes one parameter, it doesn't take two. Remember, we used to have two, a B and X. This takes one parameter, which is either an int or a function that goes from an int to an int. And of course, I return an int as a total. And if it's a left X, then here X is bound to the type int, and I can just add 3 to it and return that as my value. If it's a right X, then it's a function of int to int, and I can apply 3 to it and return that as my value. And again, note I'm getting exhaustiveness checking from my operating system. If I forget one of these, not the operating system, the programming language, sorry, will tell me I got it wrong. And even more so, if you call this function incorrectly, the compiler will catch it. In the closure version, if I passed in true and not an int, it would blow up at runtime. The compiler would accept it and just blow up at runtime. Here, if I passed in left of a function where I'm expecting an int, then this type would not be either int and something else, it would be either a function and something else, and Haskell would go, type error. Your code's wrong, fix it. So there's no way to call this function wrong. Unlike our closure version, you can't call this function wrong. So I want to add a corollary here. The time you most need static typing is exactly the time it's most tempting not to use it. I added this because I had a discussion with a couple of people and they talked about gradual or optional typing. And one of the standard complaints I get is, okay, sure, for your core code, you can statically type it. But for dealing with I/O, you want to do dynamic typing there. And my response is that's exactly backwards. In the code where a bug will allow an attacker to take over your entire system and steal all your money, you don't want to use the computer to help you there. But in the point where a lack of hostility at least can be assumed, there you want to help. Entirely backwards. So another aspect of large-scale programming is documentation. And here we start seeing the people getting antsy. In a large-scale project, documentation is even more important. Remember, we're talking about very large amounts of code here, too much code to hold in your head at any one point in time. Even more so, most of the code wasn't written by you. There were at least 2, if not multiple other people in the project writing code. So, most of the code probably isn't written by you. And even of the code that was written by you, this is a long-lived project, so it's been written long enough ago that you've forgotten how it works. So you need to document how does this stuff work, what interfaces need to be supplied, etc. At the same time, documentation is even harder in a large-scale project. More code means more dependencies, more complex interactions, thus more need for documentation. Of course, idiots in the technical sense don't document or maintain documentation, so documentation becomes out of date. And it becomes even harder to fix stale documentation simply because of the size of the problem. A 3,000-line project, it's not hard to go through, delete whole comments, and rewrite them. A 300,000-line project, that's a slightly different undertaking. So static types make a dandy and machine-checked documentation. The interesting paper I want to point people to, it's very accessible, uses almost no Greek letters, called Phil Wadler's Theorems for Free, that explains what I'm about to say. And I want to emphasize here the machine checked part of this. The nice thing about it being machine checked is you can guarantee it's not obsolete. The number one complaint I've heard from programmers about documentation is it's obsolete, the comments are wrong. If the code compiles, you can guarantee the types are correct. So that gives you some level of documentation about what's going on. So an example of what I mean. Consider a function with this type. And those of you who are paying attention may actually recognize this type as our old friend find from several examples ago. But let's ignore that. You have no names. Names are a form of documentation, remember. You have no comments. Of the entire universe of all possible functions, what functions can fulfill this type? What functions can fulfill this contract? Well, given this type, I know that it takes some set of elements from this list, and I know it passes them into this function, possibly no elements whatsoever. That's a valid implementation, but I know any value it's passing into this function has to be from this list, because the type A here can be any type at all. There's no other source for this function to get values known to be of type A other than the list of values given right here. It could be types that weren't even invented yet when the function was written. So it takes some set of values, passes them into the function, then it picks one of the values and either returns just that value or returns nothing. So it could be it returns the first value in the list that the function returns true in. Could be the first value in the list that the function returns false. Could be the last value in the list. Could be a random value in the list. So there are a number of different implementations, but when you compare the number of different implementations to the uncountably infinite number of functions that could be, you realize we have a very small number of implementations we have to worry about here. And when you limit that implementation to reasonable implementations, and when you limit that further by adding, say, a name and maybe one line of comments, now all of a sudden the number of implementations drops dramatically. So another issue in large-scale programming is code maintenance, something we seem to not like to think about. So code must change. If you live long enough, the requirements change. And if the code base is large enough, you can't just simply throw it out and rewrite it. So you've got to change the code in T2. This includes code that's called all over the place. The very common assumption I see programmers make, which is kind of surprising considering how wrong it is, that when they get done writing a function, that's it. It's done. This is how the function works and how it will work for all time. And in any large-scale project, that is just not true. There's no function you can sit there and go, this is how it will work for all time. Changing the behavior of a function is not necessarily wrong. We need to be able to change the behavior. So as an example, and I've seen this sort of, evolution in a number of different places. We start with some function that takes some set of values and it returns an int. And all is well and good. But then we hit a case where maybe there isn't an int to return. So we now need to change it so it returns a maybe int. And it returns nothing if there's no int to return. Well, then we want to change it so that it returns an error message explaining why we're not returning an int. And then, we need to return, instead of just a string as an error message, we want to return some complicated structure that we can use to put up a nice dialog box to go, why isn't there an int? So a lot of programmers will go, well, design it right in the first place. Well, you don't know, generally you don't know what the right design is in the first place You don't know what the right design is in the first place. That these changes happened because of changing requirements. How you thought things worked at the beginning are not how they work in the end. The other solution to this, by the way, which I've seen quite common, is to have 4 different functions. Hopefully I don't need to tell anyone here why that's a bad idea. So now we have a situation where a function has changed its behavior. It's returning a different type or taking a different type. What needs to get fixed? And remember, lots of code means you can't remember where all it's used, where all this function is used. And lots of developers means you may never have known where all it's used. No single person may know where all it's used, as different people used it in different places. So unit testing tells you something broke. You changed the type of the function. It's returning a different value now. Well, you know that. That's the whole point of the exercise. Of course it's returning a different value. It needs to return a different value. What else needs to change? Static typing goes, this code right here is broken. You're using the return value as an int, and it's a maybe int, and that's wrong. Here, line foo.hs, line 377, whatever. So, section number 3, multi-threading. This is where stuff gets interesting. Multi-threading is coming. And you should be looking forward to it about as much as Ned Stark is. We have switched over, actually about 8 to 10 years ago, we've switched over. Moore's law now no longer means individual single threads are getting faster. What it now means is you're getting about 2x the number of cores every 2 years or so. Wimble whatever numbers you want to stick in here, but it is an exponential thing. So we're at about 8 cores now. A decent box will have 8 cores. Actually, it's starting to get 16 now. That means in 10 years, doubling every 2 years, the same box will have 256 cores. 20 years from now, it'll have 8,000 cores. And I actually think, for long involved reasons, I could give a whole nother talk on this slide alone. I actually think for a whole lot of reasons that this sort of explosion will happen. 8,000 core machines are coming much, much sooner than you think. It's not 20 years out. I put them more like 10 years out. But if you're planning on your code, expect your code to be around in 10 years. It's not only got to run on the 8 core boxes and the 2 core boxes and the old 1 core boxes that are still out now. It's got to work on the 256 core boxes people will be buying 10 years from now. As a side note here, by the way, message passing, very good, love it to death. It's not sufficient. You need to scale. You need to efficiently scale. And you can't write, if you write your message passing to use 8,000 cores, it's not going to run very well on a single core machine. If you write it to run well on an 8 core machine, and you try to run it on an 8,000 core machine, and it's not going to run well either. Multi-threaded code is different. So yet another thing programmers are not wanting to have to deal with. We have what I call the 4 horsemen of the parallel apocalypse, and race conditions, deadlocks, live locks, and priority inversions. Not going to explain these to you. They have good Wikipedia articles on them. Look them up. The thing they all have in common are they are all very rare in single-threaded code, but you start seeing them a lot more often in multi-threaded code. And 2, they're all timing dependent. That means they're all Heisenbugs. Small changes to utterly irrelevant parts of the code changes the timings and changes how they occur and how they show up. Also, testing for them is nigh on impossible because you have to have these 2 pieces of the code executing at exactly the right time. If they're a nanosecond apart, the bug won't manifest. I've had bugs, I've had race conditions that showed up doing 100,000 tests a second. It took 4 days to recreate the race condition. but that meant our customer was seeing it every 2 weeks and was cooking a patient every 2 weeks, so I was told fix it anyways. These bugs are going to happen, and we are going to need to fix them. And fixing them is not fun. The only solution, the only way to do multi-threaded code and maintain your sanity is every piece of mutable state, and I mean every piece of mutable state, needs to come with an ironclad guarantees that either A, all accesses are properly synchronized, or that B, only one thread accesses it. Anything less leads to hell. Don't do that, doesn't work. This is the situation we find ourselves in. Sorry, this is something of a low-res picture. So what you have here, you have a couple of porta potties on the back of a truck about to go under the bridge, and the porta potties are not going to go under the bridge. Behind them, you've got the nice red convertible with the top down. You all are in the convertible. Top's down, your wind's into hair, you think life is grand, you have no idea the ton of shit that's about to land on you. And I am not kidding. How does static typing help us in this situation? Well, now we come to the dreaded M word. Ooh, scary. What are monads? Monads represent a computation producing a value performed in a domain where some condition is true. Functions are values, by the way. So, give you an example of what I mean. A number of Haskell I/O monads, some of you may have heard of these. IOA represents a computation producing some value of type A in a state where it can do I/O. Read and write files, etc. STMA is the same thing. It's a computation producing a value of type A that has to run in a transaction. STSA is a computation producing a value of type A that must run in a single thread. ST stands for single thread, identified by the type S. And that's some type hackery I won't get into. Maybe A, maybe it's a monad. Maybe A is a computation producing a value of type A that exists in an area, in a domain where it might not produce a value. Every monad in Haskell, or anywhere actually, breaks down into, you can do this exercise and go, what is the domain that monad represents? And it's actually a good exercise, I recommend it. So functions declare what domain they are in by the monad of their return type. If their return type isn't in a monad, they don't care what domain they are in. They're pure, they don't do any I/O, they don't need to be in a transaction, they don't care, they can be called anywhere. So you can have a function like hgetLine that takes a file handle and it returns a process that executes where it can do I/O, read the file handle, read the next line from the file, and return a string. Read tvar, reads a mutable variable, type A, and it returns type A in a transaction. So this function, you can only call read tvar in a transaction. Monads allow us to prove we don't have the four horsemen bugs. They allow us to enlist the type system to go, all mutable variables are either properly synchronized or only exist in a single, only are accessed from a single thread. They provide the guarantees we need. So I want to talk a little bit about software transactional memory because that's the main way Haskell, the new main way Haskell provides these guarantees. Software transactional memory was an idea that came up in the 80s, late 80s, early 90s. And the idea was fairly simple. We all know SQL databases. You can start a transaction, read a couple of tables, modify a couple of tables, commit the transaction. It all takes place atomically or it doesn't take place at all. The idea was to do exactly the same thing with mutable variables in your program. You can start a transaction, read some variables, write some variables, commit the transaction, and either everything takes place atomically or none of it does. So it sort of gives you the A, C, and I of acid. It gives you atomic, other threads can't see the intermediate states, consistent, independent, acts as if all transactions were performed serially. It doesn't give you durable. It doesn't write stuff to disk. But other than the durable, it gives you the ACI of transactions. And so this allows us to write code and compose code and know it's still correct. So a lot of people read this and came across this idea and said, hey, this is a really neat idea. This is a great idea. It solves all the problems. So Microsoft went, hey, this is a great idea. And so they put together a team. I'm not sure how many developers were on the team. I think it changed over time, but it was at least 6. And they worked for at least 2 years to add software transactional memory to C#. And they failed utterly. In the end, Microsoft just pulled the plug and said, C#'s not going to have software transactional memory at this point. Maybe in the future, but this project failed. So Simon Peyton-Jones heard about the idea and said, hey, this is a great idea. So Minion, grad student, go implement software transactional memory for me. And probably took them longer than a long weekend, but not that much longer than a long weekend. And the Minion, grad student came back and said, here's your implementation of software transactional memory. And the result was success. With such resounding success that I actually have heard, I'm not sure if this is correct or not, but I've heard that it's getting added to the next version of Haskell. That if you want to call yourself Haskell, you have to have software transactional memory. Because it's so easy to add, why wouldn't you? So what's the difference? Why did Microsoft, with 10 times as many developers and 10 times as much time, fail, and Haskell succeed? So there are 2 problems with Haskell that sort of turn it into the Full Employment Act for CS researchers, which is, 1, you start a transaction, you execute some non-transactional piece of code, and then abort the transaction. What happens? Classic example here, start the transaction, call launch the missiles, abort the transaction. Does Moscow still get incinerated or not? The other problem is, what happens when you access a transactional variable when you're not in a transaction? So these 2 problems combined turned out to be, and a performance problem, which I'm not talking about here, turned into to be the nightmare of why Microsoft couldn't implement this in C#. So how did Haskell deal with this? Well, Haskell gave you a function called atomically that takes a process that has to be executed in a transaction, producing some value A, and actually goes and executes it in the transaction. And since executing in the transaction reads and writes mutable variables, it returns its value in a type IOA. It has to be executed in a domain where you can do IO. It does not provide you a function to let you go the other direction. You can't go, here's a process that has to take place where I can do IO and execute that in a transaction. So the function launch the missiles definitely does IO. It affects the outside world. So it has to live in the IO monad. So you can't call that function from within the transaction. If you try to do it, it's a type error. And Haskell goes, I don't compile your code. Your code's wrong, fix your code. You can't call launch the missiles inside a transaction. So Haskell just didn't even have to worry about that problem. They could just do, the type checker says, if it type checks, you can't do that. So we don't have to worry about that. We don't have to worry what happens when you do that. At the same time, the only function, you have a tvar here. This is a mutable variable that can hold some type A, a mutable reference that can hold some type A. You can read and write it, but the read and writes take place within an STM monad. You can't access these variables outside of a transaction. Again, the type system prevents you from even trying to do that. Prevents you from, if you try to do it, your code simply doesn't compile. So again, the Haskell implementation doesn't have to worry about what happens if you access a mutable variable and you're not in a transaction. Can't happen, can't do that. Can't do that wrong. There's a similar trick for single-threaded access. And I'm not going to go into this a whole lot because it does deal with some of the fancier end of Haskell's type system, specifically higher kindage types for those who are interested. But again, we use monads here for very good effect. We have strefs, which are our variant of tvars. I don't know why some of them are called refs and some of them are called vars. That's an interesting question. So you can only create, read, and write these strefs in a single thread. And again, the type system prevents these values from leaving a single thread. Allows you to prove this mutable variable is only viewable, only accessible from a single thread. So you might think monads are kind of scary, but this is what you should be thinking. Yes, they're scary, but they're the defender we really need. Plus, they have a really cool utility belt. Or maybe not that scary after all. So, almost done. Last thing I want to cover here is static types versus Lisp macros. One of the legitimate complaints you might make is, okay, static typing makes a bunch of advantages, but if it requires you to not do something that's an even bigger advantage, it can still be a negative. And generally, the even bigger advantage I've heard is Lisp macros. I do have to say, Lisp macros are nice. So, to a first approximation, statically typed languages don't use macros. I mean, I can wimble on about template Haskell or Camel P4, but to be brutal about it, Haskell programmers and OCaml programmers use macros less frequently than C++ programmers use the C preprocessor macros. And there's a reason for this, and it's an interesting reason in my opinion. Haskell and Lisp are alike in that they're completely different from most of your other normal languages. In languages like C++ and Java, you have code and you have data, and these are two completely different things. And basically, never the twain shall meet. They can reference each other, but they're two completely different things. Both Lisp and Haskell go, no. Code and data are the same thing. The interesting thing is, they mean completely different things. Lisp and Haskell mean completely different things by code and data are the same. So Lisp says all code is data. A function is nothing more than a list of operations to be performed that can be operated on like any other list. So this gives you two very big results to this. The first is the homoiconic representation, S expressions. You have to express your data, you have to express your code in the same form you express the data because it's the same thing. So parentheses come out of this pretty quickly. The other thing is macros. All a macro is it's a function that operates on a data structure that happens to be code, as opposed to data, because there is no real difference. And in fact, you can use them, you can blur the line there. Haskell, on the other hand, goes, all data is code. You don't have an int in Haskell. Well, occasionally you do, but to a first approximation, you don't have an int in Haskell. You have a hunk of code that when executed produces an int. When you add two ints together, that just creates a new hunk of code that when executed, evaluates the first two hunks of code and then adds the results together to produce its result. So Haskell, this leads very quickly to two big things, one of which is lazy evaluation, which is what I just described there. The other of which is combinators. In Haskell, add plus is a combinator. Takes two, all a combinator is it's a function that takes functions and returns other functions. So add takes two functions that produce ints and returns a function that produces ints. So I could make a very strong case that Haskell is actually combinator-oriented programming. And if you've ever looked much at Haskell code, you will discover they love them some combinators. There are all sorts of combinators. Not just, monads are the example everyone thinks of. Monads are a combinator. Well, technically the bind function of the combinator, but there are a whole slew of them. Now the important thing is, these two, it's a function that takes a function and returns other functions. So it's a higher order function. It's a function that operates on functions. So these two approaches are actually approximately equally powerful. And I say approximately because there are some things that are easier to do in one than in the other. And that works both ways, by the way. I have some Clojure code that is seriously heavy, 3 levels deep of combinators, functions that produce functions that produce functions that produce functions. Debugging it becomes really fun in a bad manner. But also you can do, most stuff you can do in one, you can do in the other. The canonical example is the OR function. How do you implement short-circuiting OR? In a macro, it's easy. You just take care where you actually evaluate your arguments. In lazy evaluation, again, it becomes easy. You just be careful about where you force the values. So, almost done. In review, static type gives you reduced bug fixing time, no more null pointer exceptions, machine checked documentation, some protection against idiots, including yourself, maintainable code, protection against the 4 horsemen of the parallel apocalypse, powerful abstractions, but most importantly, it gives you working code sooner. And that's the whole point. So that's it. Do we want to take functions, or
let's take a couple of questions now, and then we'll have a short break.
Okay. Any?
That was a great talk. As much as I'd love to use Haskell in my day job, my employer won't let me. So,
yeah.
My question is, what advice can you give for those of us who have to use C++? Can we take lessons from Haskell?
What? Okay, so the question is, what advice can I give for you if your boss forces you to program in C++ or Java or some other horrible language? The first piece of advice I would give is you should be programming not just at your job, but as a hobby as well. And when you're programming as a hobby, you can, what your boss's opinions are can take a long hike and off a short pier. So my opinion is 20 years from now, we're facing a sea change. 20 years from now, most programming will look a lot more like Haskell than it will like Java. This is very similar to the sort of programming, the sort of sea change that happened between the mid-'80s and the mid-'90s as we switched over to object-oriented code. And I could make a very strong argument that, learning, if it's 1985, learning Smalltalk is a really great career move. Not that Smalltalk is used all that much now either, but it's all of the languages that are used look much more like Smalltalk than they do like Fortran. So that would be my first piece of advice. My second piece of advice is take that into consideration in your next job. So another question?
Can you very briefly comment on the difference between STMs in Clojure and STMs in Haskell?
Can I comment on STMs in Clojure and STMs in Haskell? I haven't looked at the most recent version of Clojure, so there are a couple of capabilities Haskell has that Clojure doesn't have. The biggest problem is just ensuring correctness. And we have hit multiple problems where we were doing I/O in a transaction and didn't realize it because we were doing the transaction up here and the I/O down here, and one person was writing the transaction and somebody else was writing, oh, I can just do I/O here. And then the I/O gets done multiple times and you're like, why is this record in the database 3 times? Oh, it's because it's in a transaction. So that's the problem you hit. Oh, another question?
I just want to say, I know a lot of people have had success getting functional programming at their job by
by using another language on the same platform for testing? It's like
that's a good point. He just wanted to comment. I'm repeating, by the way, for the record, that a lot of people have had success sneaking functional programming into their job by just using a language that runs in the same platform. For example, if you're on Java, I comment that both Clojure and Scala compile to jars. So you can just hand jars off to your IT people and go, no, really, it's Java, really it is. Just run it like Java. Although I do have a humorous story of a friend of mine who tried pulling something like that. And a problem with functional programming is that it tends to allocate a lot. And so he wrote a program, and it had a working set size of about 4 megabytes of heap. So in their, it was at a big corporation, so they had this whole thing to deploy the program. And one of the things was, how much heap size do you need to give it? So he said, give it 8 megabytes of heap. So what was happening was, it would allocate 8 megabytes of heap, run out of heap, do a garbage collect, drop back down to 4 megabytes, and start allocating again. Well, the testers saw this and said, oh, he's not giving it enough memory. So let's give it 16 megabytes of memory. So what would happen is it would allocate up till it hit 16 megabytes of memory, hit a garbage collection, go back down to 4. Okay, let's give it 32 megabytes of memory. Okay, let's give it 2 gigabytes of memory. Okay, now we have a problem because we give it 8 gigabytes of memory. First of all, we're running out of memory. Second of all, it allocates all 8 gigabytes of memory and then hits a garbage collection and stops for 2 seconds while it goes back down to 4 megabytes. And he was like, no, just give it 8 megabytes. It's happy in 8 megabytes. So he had to do that fight. So there are downsides to doing that, but in general, it works fairly well. So, any more questions?
Having heard this for the second time, and even better on the second go through.
Thank you.
You mentioned in your previous talk how, in a sense, you got a message passed to you when you were expecting a function. Or was it, or in a sense it was a function. It was a message when you were expecting a function. And that was in a sense one of the disasters that you...
So in a previous version of this talk I had an example, and I forget what the example was, but it was a case of getting past something that was almost right but not wrong, but not totally correct, and stuff blowing up in amusing ways. And I hate to say I actually have forgotten what that example is.
Compelling example.
So, okay, I'll try to remember it and add it to the next talk. Any other comments, questions? Rotten fruit? Okay.
All right, guys. I think we'll take a couple minutes break here, and then we'll come back to Gersham's talk.